So let's start. We are now on record. Okay. So we talked about convexity last time, and we're now going to see how that plays out when we have differentiable functions. And now remember that differentiable functions in general simply mean that if you are looking at some point and you are looking at very closely on that point, then you can approximate it linearly. And this, on the other hand, means that in geometric intuition of that is that if you have a function that maps like a surface, of course, this is still not necessarily accurate intuition in the more general spaces, but think that the function maps a surface. And if it's differentiable, then if you zoom in very closely to that, then that surface is locally flat, right? So because, barring, under the assumption that the flat earthers are wrong, if the earth is roughly spherical and it is pretty much differentiable, I mean, at least pretty much, then what would happen is that if you look at it very closely, then it would be flat. It would look flat locally if it's differentiable, right? And the circle we know is differentiable, so locally a circle looks like a flat surface. All right, if we have a convex function, well, if we have a differentiable function, continuously differentiable function, then what happens is that the functions change from f of x to f of y when we move from x to y. From y to x. This is so when we move from y to x, then what happens here is that the proportionate change is always, the true change is always greater than that indicated by the derivative. It means that if there is curvature, then the curvature is, always upwards. That's what convex means. It's always upwards. If we look at the surface, this is geometric. If we look at the surface, then locally, if you approximate it with a flat surface, then what happens to the true surface, it curves upwards, right? So when you move from y to x, then the function is actually greater than if you try to move from y to x in a linear fashion in a straight line. That's what convex means. Well, that's what convexity means when we have a differentiable function. And that we can get from that theorem here. So let's say we are now going to be using the theorem in that that we had, the mean value theorem. So we move from y to some point between x and y, right? So if alpha is 1, we move to actually directly to x, right? You see here, the key here is this here. Compare that to the derivative x plus h, but in here we are moving from y to some point between x and y. If alpha is 0, we remain at y. If alpha is 1, we go to directly to x. And now, because of differentiability, it's the same as f at y plus then the derivative at, this is mean value theorem, at some point between x and y, some point between y and alpha times x minus y, z. So this is the mean value theorem applied here. And now, because this is linear, we get this alpha outside as a coefficient. Now, we can combine these two with the convexity here, because we got from convexity, we get that f at this y plus alpha xy must be smaller than or equal to f at y plus alpha times f at x minus f at y. This we get from convexity by a minor algebraic reorganization. So we can apply this part to convexity, and we get that this left-hand side is smaller than that right-hand side. Fy cancels out, so alpha can be divided out here, and Fy's cancel out, so we get that f prime z is x minus y is smaller than or equal to f x minus fy. Now, as we let alpha go to 0, then z goes to y. And we get the result that we were proving. So then the other direction we can use that, if this is true for all x and y, then we can use the approximation in the other direction, and we get here that the convex combination, we get the convexity result. I'm not going to go through the convexity result here. You know, it's more interesting that if it's convex, then this holds also, because we are going to be using that more. If this holds, it's convex. That's also fascinating, but not quite as useful. So, sorry. Another thing that comes from this is that if we have that f of x minus f of y is always greater than f prime at y times x minus y, then f is strictly convex. That can be proven using the same template. Going to use the second derivative here. So I'm not sure if you are familiar with matrix algebra. Did you take that course beforehand? If you didn't, then you don't know what positive definite mean. So very quick explanation of what positive definite means. Positive definite means that if you have a matrix, now let's think in terms of matrices again. We could, it's true for all, I mean, the definition is the same for all bilinear forms, but for matrices, we say that A is positive definite. You won't see this text before I finish it. If for each x transpose, okay, so this is really bad. I use the prime to indicate the transpose. So if we multiply matrix X, matrix A with any vector from both left and right, then it's positive definite if for each x prime A x is greater than or equal to 0.
Sorry, we don't see it.
The annotation is not visible.
No.
It's not, you don't see it?
No.
At the bottom of the page?
No.
No, okay. Ah, okay. Oh, okay. I'm sorry, for some reason it's not working. But positive definite, well, positive definite means basically, now let's think in terms of matrices. A matrix is positive definite if and only if you take a vector x transpose A, x is greater than or equal to 0, regardless of what x is, and it is equal to 0 only if x is 0. That's what positive definite means. If you've taken up matrix algebra, you will also know that it's positive definite if all the eigenvalues of the matrix are positive. I mean, I'm not sure if you remember the eigenvalues of matrices and so forth. So I think this was recommended recommended prerequisite was matrix algebra. I'm not going to ask this in the exam, but it does help you in understanding. We'll go through this in exercises. We'll look at a little bit more about how positive definite means. But if you don't know what it means, then you should definitely look it up now. In other words, positive definite in this situation means that this term here, now, you see the annotation, you see the drawing, right?
No.
The drawing is not shown.
No.
So none of the drawings that I were making before, you were able to see none of them.
No, only for this page.
It's not showing for this page now. You're not seeing this drawing.
No.
No.
Okay, let me try
The
to
two previous were visible.
Okay. So there's something wrong. Just a second. I'll pause the record. So basically, positive definite means that if you have a bilinear form, in this case it would be a matrix probably, and you multiply it with some vector from both left and right hand side, then that result is greater than or equal to 0, and it is exactly 0 only if the vector you multiply it with is 0. So in this case, x minus x0 and x minus x0 is applied twice to this bilinear form. And again, it's easiest to think of this bilinear form as a matrix, and you multiply it with from both sides with the same, so it's a square matrix, and you multiply it from both sides with the same vector. This is going to be positive. This is going to be positive. And that means that if you rearrange the terms, then the change in f of x minus fx0 is going to be greater than f prime at x0 times x minus x0. And it simply means that if we can find a region, if you are talking about optimization problems, the way we are going to be using this is we have a function, let's say we have, forget the constraints now, if you have a function whose Hessian, that's the second derivative, it's a Hessian matrix, if it's positive definite in all the points in some region, then we know that it's convex in that region. And if we find the 0 of the gradient in that region, then we know that that's the minimal. It's the convex. All right. Here are some examples. Here's x to the 4. It's it's going to be strictly convex, x to the 4. We can show that later, but it's not positive definite because it has the second derivative has a 0 at 0. Well, that's just one point. Everywhere else, it's a positive definite. Here's an example. Now we calculate the first derivatives and the second derivative. So we have a function that is defined as 2x plus 6y plus 2x squared plus 3y squared minus 4xy. We calculate the Hessian, so that would be the second derivative. And we get this matrix, which consists of 4 minus 4 minus 4, 6. The way you can calculate whether it's positive definite is you find the eigenvalues. We'll talk about this in the exercises a little bit. You can use this actually, you can do this with MATLAB, and I probably maybe I should show you how to do that. Just a second. So the way we can do this with MATLAB, for instance, and I'll wait until the MATLAB, I can do the, where's my MATLAB? Where's my MATLAB window? Over there. So let's share that. Here's MATLAB. Okay. So I'm going to write that matrix here. So we can do this. H is equal to 4 minus 4 minus 4, 6, right? And then we calculate the eigenvalues of that. And we get two eigenvalues, 0.8769 and 9.1231. So those are both positive. And we know that it's this matrix is positive definite. So because it's the Hessian of that, by the way, I can show you how to calculate the Hessian directly. So I'm going to have x, y, which are real. And then I'm going to define fx, y as 2x plus 6, 2 times x plus 6 times y plus 2 times x squared plus 3 times y squared plus minus 4 times x times y. And now I can calculate the Hessian of f, which gives me this matrix that we had. Okay? So this is really something that you can use MATLAB to calculate. Okay, let's go back to the material. I just wanted to handle this, so that you know how to do it. If we have what is called the positive semi-definite, now positive semi-definite means that it's x, I mean, you know, it may have zeros somewhere. So the if you think about this in terms of the Hessian, then the Hessian may have zeros. The eigenvalues may be 0 at some points, but they can never be negative. And the proof is fairly simple because if it's positive semi-definite, then you know, there is equality at some point. I mean, strict convexity follows from positive definity of the Hessian, and then convexity follows from positive semi-definity. Of course, it may be strictly convex even if the Hessian is positive semi-definite, but if it's positive semi-definite, we cannot rule out the possibility that the inequality there, which strictly convexity means that it cannot be equal, that it's sometimes equal. That's the thing. Here are some examples that you can do with MATLAB. There's a R3 problem. You can do this. Here you can see what is written. I urge you to do this yourself. You can write here real if you want to stress that any computation is done under the assumption that these variables are real. If you assume that they are real, then MATLAB doesn't give you, for instance, complex roots as solutions to certain situations and so forth. You can calculate the Hessian and so forth like this, and the eigenvalues of that. This can be done symbolically so that they depend on x. So for instance, in this case, this is simply going to be what the MATLAB will output. So not going to go through this in detail, but here's a Hessian. If you calculate the Hessian's eigenvalue, you notice that symbolically it results in something that has also the squared here. So we can verify it still contains the symbol x1. So in order to answer whether this is positive semi-definite, this has to be positive. This is just a number, and it is positive. I mean, the square root of 17 is something in the order of, well, it's definitely under, it's a bit over 4, but not much, definitely under 5, because 4 squared is 16 and 5 squared is 25, and it's 17, so, sorry, yeah, 17 square root is a bit over 4, so 5 minus that is definitely positive. And this is adding 2 positive numbers, so that's positive. And if x1 is, regardless of what real value it obtains, this could be 0 when x1 is 0, but otherwise it's positive. So this is positive semi-definite, and definitely it's convex. don't know, don't care if it's strictly convex. It's probably it is strictly convex, but that's not what was asked here. So now the theoretical content, that is the important part here. So when we have convex functions, why do we need them and why do we want them? Well, one thing why we want them and need them is that we want these convex functions because optimality is easier to establish. Intuitively, if you think about this, that geometrically speaking, that if you have a function that is convex, it curves upwards. Whenever you're approximated, it tends to curve upwards. Meaning that once you hit bottom, that's as low as you can get. Because it won't level out and then go back down. Convex means that it's smoothly curving like this, upward curving. So of course you may go down, but then once you start curving, you go up again. So that's the intuition there. So convexity is really cool for optimization purposes. So if we have an open convex set, meaning that the set which is our admissible set or the feasible set, the set we are talking about, doesn't have these pathological situations like a outward protruding edge like this that curves like this, so that it's not convex. So let's say that it may have weird shape, but it's convex. If our region is convex, and we have a function that is continuously differentiable and convex in that, so I tend to say well behaved for a function that is continuously differentiable. So it doesn't have, sharp edges, and it doesn't have infinities, right? So it's continuously differentiable, at least when we are inside that set. If that is true, then f has a global minimum, and the global minimum at point x star, if and only if, whenever you approximate it with the derivative and you move from that point to any place, then that change is greater than or equal to 0. So what does it mean? Let's look at this proof. This proof is important. So let's say that we have f prime and x star. That's our derivative. And now this is a vector function. So this is basically, think gradient if you want. And you take a change from that point to any direction. And then f prime dot product in that direction is always greater than or equal to 0. What does it mean? It means that you have reached a point from which, if you move to any direction, then either you don't change f at all. This is the linear approximation given by the derivative. So if judging from the derivative, if you moved into any direction, it either moves positively or doesn't move at all, no matter where you try to go. Then by theorem 2.8, which we just proved, the actual change is going to be greater than that, meaning that the function f of x will be greater than f at x star, regardless of where you move from x star. So that simply means that this is the point at which it is smallest, the value. On the other hand, let's assume that it's a global minimum. Maybe there's a point that doesn't satisfy this, or maybe there isn't. Let's see. Let's say that we have a global minimum. It means that whenever we try to move anywhere from x star, then it's smaller than any point. In particular, if we are moving towards some point x, and we're moving along the line x star minus alpha, line from x to x star. So here's x star, and we're moving to x star over there. And we're moving along the line. So let's say we take alpha x star plus alpha times x minus x star. So at alpha equals 0, we are at x star. And at alpha equal 1, we are already at x. And because this is a minimum, then although at all those points, this function gets a value that is greater than or equal to the point at this minimum. That's what minimum means. It's the smallest of all. So there may be equal points, but definitely not points at which f of x is smaller, right? And we can write this in such a way that if we divide this whole thing, this quotient is positive. Sorry, this quotient, not quotient. The difference between these is positive. So if you subtract from this larger one, the smaller one, it's positive. Remember, alpha is between 0 and 1, so it's positive. So this difference quotient here is going to be positive. And if we let alpha go to 0, then what we really get is a directional derivative. We get the directional derivative in the direction of from x star to x at x star. And this gives us that there's, this is from the theorem that we discussed, the directional derivative. It's simply the same as the gradient's dot product with the vector into which we are moving, which is then the f prime at x star times the vector x minus x star. So this is an if and only if. So what does it mean? Well, it means that if we find a critical point of f, meaning that a convex function, if we find a critical point, meaning that it's the gradient is 0, then we've actually found a global minimum. There you have it. So really, minimizing of convex functions without any constraint, unconstrained minimization of convex functions is tantamount to finding the 0 or a 0 of the gradient, because if we find that point, then we're done. That's what it says. Find the 0 of the gradient and you're done. That's the minimum if you are dealing with convex function. So with convex functions, optimization is actually pretty easy. That's why we talked about convex functions, and we want our functions to be convex if we are to minimize them. Here's an example. Let's say we have a symmetric positive definite matrix, and let's say we have this what is called a quadratic form. It's defined like this. So f of x is defined as 1/2 times x transpose ax plus b transpose x plus c. Now, if we calculate its derivative, we can. It was done in example B24. If you want, you can do that, but you can also do that by hand. Verify that that's the second derivative. It's simply that matrix A. Because it's positive definite, then this is strictly convex. And using this corollary, the global minimum is a 0 of the gradient, and we can just solve this by finding the negative of A inverse B. So this means that quadratic functions have a very easily calculated minimum, even when we deal with from Rn to R. And in fact, when we have this one method later we will discuss that you can actually what you actually can do is you can approximate a function with this quadratic form, find its minimum, and then approximate it again, and so forth and so forth. So in fact, this is a very useful result, even though it's just given a role of example here. The thing is, if we have a convex function, one that is not necessarily differentiable, that is defined on a convex set, and from that convex set to the real numbers, then if we have a local minimum, then the local minimum is also a global minimum if we have a convex function. And that's not actually that hard to prove. So let's look at this proof. Again, we use this alpha instead of lambda. So let's say x0 is a local minimum. We do this with a indirect proof, assuming that it's not a global minimum. So if it's not a global minimum, then it's locally minimum, meaning that in the small regions outside that there are values smaller than that. But there is somewhere, sorry, the value is only bigger than x0 or equal to, but there is some y a bit further off where f of y is smaller than f of x0. Because f is convex, we can calculate the value at each intermediate point between x0 and y. And we use the convexity result so that at that point, we use now alpha instead of lambda. Alpha x0 plus 1 minus alpha y, the function is smaller than or equal to alpha times x0 plus 1 minus alpha times fy. So that's going to be definitely, if f at y is smaller than f at x0, then this is smaller than f x0. But we assume that this is locally minimum. It means that even if we move just a little bit from x0 towards this y, then it should decrease already. So it cannot be local minimum. So that's a contradiction. So, if it's a local minimum, then it's a global minimum. These proofs are not terribly hard. You should go through this to understand what is going on. You can draw a picture here. So it means here is that, okay, let's say that this x0 is, let's say that's my x0. And here is my point y. And now local minimum means that in some surroundings of x, it's the smallest. But because it's convex, then when we move from this x0 to y, then in fact, in all these points, it must go down and then up. And if it's smaller at fy, then we can prove that it's, even if we move just a little bit, if we move here, then the function should be smaller than the function in here. But that's definitely not going to be true because we assume that this is a local neighborhood of x0 in which it is greater than or equal to at the x0. So it's a contradiction. It must be a global minimum. All right. And the thing is, if it's strictly convex, then if it has a global minimum, then the global minimum is unique. For strictly convex functions, so for convex functions, a local minimum is a global minimum, but there may be many of them. Think about, again, an R2 function that is, draws a surface. So if it's convex, it may be like a valley like this, but the valley may be flat along this line. So you have like a parabola here, but then it's just a flat valley like this. So you have a minimum, it's convex, but you have a minimum, and at the bottom there's actually a straight line along which you can move and maintain that same value of f. But if it's strictly convex, then it has just one point at which it is minimum, and then it grows, the function grows in every other direction. So if we have two global minima, then we come to the conclusion that the strict convexity is broken, right? So we conclude that x must be y. Okay, that's it for today. We got through this problems, to this section 2. We'll look at this exercises in this week's exercises, this chapter 2 exercises. We'll talk about linear optimization tomorrow. This is going to be a little bit, I'm rushing this a little bit because I want to get a bit ahead, and then I'll slow down when we get to the more harder, the more methodological stuff. We'll talk about the history a little bit also on tomorrow's lecture's beginning. Also, we'll have a bit more interaction tomorrow because tomorrow we have more time now that we got through this. This schedule was a bit packed for today. I only had 3 minutes of air in my schedule, so we're going to stop at 11:45 in any case. What I would like, I'm going to stop the recording now so that if you have any